Guys, in this video we're going to be talking about the solid state of matter, and our goal is to define the different types of solids that we see in nature. And we want to be able to characterize the main physical properties of these types of solids. Typically the melting point is what we want to understand in terms of the way in which these solids are put together and the types of interactions that hold the solids together. Okay, so crystalline solids are composed of crystals that have a well-defined three-dimensional structure. Okay, so you can think of the atoms if you're talking about an atomic solid, or molecules if you're talking about a molecular solid. These molecules or ions, they are occupying positions within a lattice of atoms and molecules that is very well defined, and it repeats itself throughout space. So crystalline solids have a well-defined three-dimensional structure involving the molecules and atoms that make up the crystal. You're going to find that most of our ionic compounds and metals, as well as compounds consisting of small molecules, they form crystalline solids. Other types of substances, they don't form a particularly regular solid. They form what's called an amorphous solid, where at the molecular level you can think of the atoms as being somewhat disordered. So compounds like glasses fall into that category. So some ionic compounds do this. Typically, compounds where the molecules are very large, they may form amorphous solids. Or if you've got a solid consisting of a mixture of molecules that don't quite fit together so right, they may form an amorphous solid. Here's a cartoon representing the difference between a crystalline solid and an amorphous solid. Here in the crystalline form, you can see that every atom or molecule is in its place, whereas in the amorphous solid, it's not so well organized. And so you get a disorganized structure. There are four types of solids, substances, that we'll identify. Different ways of classifying the solids, I should say. So molecular solids are solids where you have the molecules are being held together by intermolecular forces. So like the London dispersion forces, or dipole-dipole interactions, or hydrogen bonding. These are examples of molecular solids. Metallic solids are basically metal cations that are held together by a delocalized sea of valence electrons, where none of these valence electrons are attached to any particular atom. They're essentially shared by all of the atoms in the metal. Another type of solid is the ionic solid. This is where you have cations and anions that are held together by Coulombic interactions, so opposites attract. And then the last type of solid that we'll talk about is the covalent network solid, where all of the atoms that make up the solid are held together by covalent bonds. Okay, so we have molecular solids, metallic, ionic, and covalent network solids. Here's some graphics representing the different types of solids. So an ionic solid, you'd have something like sodium cations and chlorine anions that sort of form a crystal structure where every chloride is surrounded by a sodium cation and every sodium cation is surrounded by chloride ions. In a metallic solid, you basically have just this crystal of metal cations surrounded by valence electrons. Here, these cartoons, they represent molecular solids. So here in carbon dioxide, you've got individual molecules of carbon dioxide that are packed together in a crystalline structure. And what holds the molecules in the crystal are those London dispersion interactions. Right? Carbon dioxide is a nonpolar molecule, and so that's all we have here. Same thing for solid iodine. The iodine molecules are diatomic, and they're held together by intermolecular interactions in the crystalline solid. Here are some examples of covalent network. So diamonds, for example. Diamonds consist of, pure diamond would consist only of carbon atoms, and each carbon atom is bonded to 4 other carbon atoms, and it just forms this crystalline structure that extends out, and out, just, endless carbon-carbon bonds. Silicon dioxide, so this is essentially, what we know as quartz or glass, consists of silicon and oxygen atoms that are covalently bound together, forming a crystalline structure. Here's some other examples: silicon carbide and graphite as well. Graphite is particularly interesting. You've got both covalent bonds forming these layers, this honeycomb patchwork of carbon atoms, and then the different sheets of graphene is what they're called. These graphene sheets are then connected together through intermolecular interactions. So you've got covalent bonding within the sheets, and then the sheets are held together by intermolecular forces. London dispersion forces, for example. Here's just some more pictures of carbene. So here's the graphene sheet. Graphene sheets can be stacked like they are in graphene, or you can imagine rolling them up to form these nanotubes, or curving them into these buckyball type of structures that you see here. Carbon can do some pretty amazing things. So what we're being asked to do here is to classify what type of solid we would get for these different compounds. So we need to be able to look at the chemical formula, decide what type of compound it is, and then decide what type of solid structure it would form. Ammonia, part A, is a molecular compound, and when molecular compounds form solids, they form these molecular solids that are held together by intermolecular forces. And in the case of ammonia, it would be London dispersion forces and dipole-dipole coupling. Ammonia is a polar molecule, so there would be a dipole moment here, and the dipole moments would interact, keeping the molecules in the crystal. Cesium is a metal, and so it's metallic bonding, so it's going to be a metallic solid. You would have cesium cations, positively charged, and then they would be surrounded by a sea of valence electrons that don't belong to any particular atom. Cesium iodide is going to be an ionic compound. You've got a metal paired up with a nonmetal, so the cesium is going to be a +1 cation. The iodines are going to be negatively charged anions, and these guys are going to be held together by strong ionic bonds. Those Coulomb interactions will keep the solid together. Silicon is an example of a covalent network solid. So silicon, like carbon, I should say the structure is very similar to carbon. It's going to look very similar to this. Each silicon atom is bonded to 4 other silicons, and it just spreads out like that. And so the bonds are very strong, and so silicon is going to be a very hard substance, just like diamonds are. Zinc, again, is going to be a metal, so the situation is very similar to cesium. Sodium iodide, that's an ionic compound, so it's going to be similar to cesium iodide. Silicon carbide, we've actually already seen that one. This one here, it's going to be a covalent network solid. So the carbons and the silicons are going to be bonded together through covalent bonds. Methane, a molecular compound, and so when the methane forms a solid, you're going to have methane molecules that are packed together, and they're going to be held together through van der Waals or through London dispersion interactions. Some of the properties of these different categories of solids. Well, ionic compounds, since the ionic bonds are very strong, ionic compounds tend to be very hard. Likewise, they have very high melting points. They're also brittle, so that when you hit them with a hammer, they just break apart into little pieces. They don't deform like metals do. And generally speaking, in the solid state, the ionic compounds are thermal insulators. and they are also insulators for electricity as well. They don't conduct electricity or heat very well. Metallic solids, on the other hand, they're shiny, they're malleable, so it's easy to bang them into different structures. They're ductile, so that means you can pull them into wires. They're good conductors of heat and electricity, and the reason for that is because the valence electrons in the metal aren't attached to any particular atom, so it's easy to push them around with an electric current or with a voltage. Their properties like hardness and melting point vary quite a bit. It really just depends on what metal you're talking about. There are some metals like gallium that'll melt in your hand. Mercury is a liquid at ordinary temperatures. Some metals like iron are very hard. Other metals you can cut with a butter knife. So it really just depends on what metal you're talking about. Covalent network solids are very strong and very hard. They don't conduct electricity very well, and because the covalent bonds are so strong, the covalent networks have very high melting points, so you have to heat diamonds up pretty hot to get them to melt into molten carbon. Molecular compounds, on the other hand, because the molecules are held together with relatively weak intermolecular forces, they tend to have low melting points. They're usually insulators, and their hardness and stuff, it varies. It really just depends on what molecules you're talking about. Anyway, so these are the different properties of solids, and you want to be familiar with these properties so that you can do things like this. Rank the following elements in order of increasing melting point. Okay, so we're looking at silicon, hydrogen, and lithium. Which one's going to have the highest melting point? It's going to be the silicon. The reason why is that silicon forms a covalent network solid, okay? And in order to melt silicon, you would have to break those covalent bonds. And covalent bonds are very strong. So silicon is going to have the highest melting point. Hydrogen, in its elemental form, consists of diatomic hydrogen molecules. And so it's going to form a molecular solid. Molecular solids are held together by weak intermolecular forces, and so the melting point of the hydrogen is going to be very, very low. It's going to be very easy to melt molecular hydrogen into liquid hydrogen and then to boil it into hydrogen gas. Lithium is going to be in the metal. I don't know if it has a particularly high melting point as far as metals go, but it would definitely be in between the two, in between the silicon and the hydrogen. For part B of this, which type of solid is formed from these substances? So we've got ethanol, which is an alcohol. This is a molecule, and so it's going to form a molecular solid, as is methane. Methane is going to form a molecular solid. This is methyl chloride. You see that it's all non-metal atoms, and so it's going to be a molecular solid as well. The magnesium sulfate, this is an ionic compound, right? It consists of magnesium cations and sulfate anions, and so it's ionic. Which of the substance would have the highest melting point, and explain your reasoning? I'm going to go with the magnesium sulfate, because in order to melt that, you have to break the strong ionic bonds. Those Coulomb interactions between the ions are very strong, so it's going to be the most difficult to melt. So this is going to have the highest melting point. Between the other three, we've got all molecular compounds, and so we want to start thinking about the intermolecular interactions that we looked at in a previous section. Methane is nonpolar, and so it only has London dispersion interactions. The other two species, the ethanol and the methyl chloride, are both polar, so they both have dipole interactions. But in addition to the dipole interactions, the ethanol is also going to be capable of hydrogen bonding. Okay, so the next highest melting point is going to be the methanol, and the lowest one is going to be the methane, and then the methyl chloride we would expect to be in between methane and the ethanol. Well, I'm going to go ahead and stop this video here, and we'll talk about the lattice structures, our last set of topics, in the next video.